When preparing an electrical bid, consider all aspects of the project, including equipment loads, code requirements, and permits. The cost of permits and specific equipment, like display cases, should be factored into the initial bid to provide an accurate project estimate. Let's look at a scenario where display cases require 4 times 20 amps, which totals 80 amps. A walk-in cooler requires 20 amps. The saw requires 20 amps. The air conditioning unit requires 60 amps. Countertop circuits require 6 times 20 amps, totaling 120 amps. Adding these loads together, 80 amps for display cases, 20 amps for the walk-in cooler, 20 amps for the saw, 60 amps for the air conditioning, and 120 amps for the countertop circuits, results in a total load of 300 amps. It is crucial to ensure that the electrical panel can handle this load. According to electrical codes, the load should typically not exceed 80% of the panel rating. Therefore, a 200 amp panel might be insufficient, and a larger panel, such as a 300 amp panel or even a 400 amp panel, may be necessary to comply with code requirements and provide adequate capacity for the deli's electrical needs. This larger panel will incur additional costs. Obtaining electrical permits from the local authority usually involves fees that should be included in the bid. An incomplete bid may seem lower initially, but it can lead to unexpected costs later on. Consider a scenario where one bid does not include the cost of display cases and permits. While it may appear more attractive at first glance, the additional expenses for these items will likely make the final cost higher than a more comprehensive bid that includes all necessary equipment and permits from the outset. It is important to be thorough and transparent in the bidding process to avoid surprises and ensure client satisfaction. Estimating electrical work requires a detailed understanding of electrical systems, National Electrical Code, local regulations, and the specific requirements of the project. Firstly, review the project specifications and drawings thoroughly. This includes understanding the scope of work, the types of electrical systems involved, and any specific requirements outlined by the client or architect. Secondly, calculate the load requirements. Determine the total electrical load for the project, including lighting, equipment, and appliances. This calculation will help determine the appropriate size of electrical panels, wiring, and other components. Thirdly, identify all necessary materials and equipment. Create a comprehensive list of all materials and equipment needed for the project, including wiring, conduits, boxes, fixtures, and electrical panels. Be sure to include quantities and specifications for each item. Fourthly, determine labor costs. Estimate the number of labor hours required to complete the project. Consider factors such as the complexity of the work, the size of the project, and the skill level of the electricians. Fifthly, factor in overhead costs. Include overhead costs such as insurance, vehicle expenses, office supplies, and other administrative expenses. These costs are typically calculated as a percentage of labor and material costs. Sixthly, add a profit margin. Determine your desired profit margin for the project. This should be a percentage of the total project cost, including materials, labor, overhead, and other expenses. Seventhly, obtain necessary permits and licenses. Research the permit and license requirements for the project and include the associated costs in your bid. Eighthly, review and finalize your bid. Before submitting your bid, carefully review all calculations and estimates to ensure accuracy. Make any necessary adjustments and finalize the bid amount. Ninthly, consider any potential challenges. Identify any potential challenges or risks associated with the project, such as difficult working conditions or tight deadlines. Factor these challenges into your bid to account for potential delays or cost overruns. Finally, be clear and transparent. Present your bid in a clear and transparent manner, outlining all costs and assumptions. This will help build trust with the client and increase your chances of winning the project. When bidding on electrical work, it's essential to stay competitive while ensuring profitability. Researching average prices for similar projects in your area can provide valuable insights. Consider factors such as the complexity of the project, the location, and any specific requirements that may affect the cost. Staying updated on industry trends and pricing for materials and labor is crucial for accurate bidding. Networking with other electricians and contractors can also provide valuable information and insights into local market conditions. Be prepared to justify your pricing and demonstrate the value you bring to the project. Highlighting your expertise, experience, and commitment to quality can help differentiate you from competitors. Always prioritize accuracy and transparency in your bids to build trust with clients and ensure fair compensation for your work. Regularly review your bidding process and make adjustments as needed to improve your efficiency and profitability. By carefully considering all factors and staying informed about market conditions, you can develop competitive bids that help you win projects while maintaining a healthy profit margin. The National Electrical Code, or NEC, plays a crucial role in electrical installations and safety. It provides a comprehensive set of standards and guidelines for the safe installation of electrical wiring and equipment. Compliance with the NEC is essential for protecting people and property from electrical hazards. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It is updated every 3 years to reflect changes in technology and best practices. Electrical inspectors use the NEC as a reference when inspecting electrical installations to ensure compliance with safety standards. Understanding and adhering to the NEC is essential for electricians, contractors, and anyone involved in electrical work. It helps ensure that electrical systems are installed safely and reliably, reducing the risk of fires, shocks, and other electrical hazards. The NEC is developed and maintained by the National Fire Protection Association, or NFPA, a non-profit organization dedicated to reducing fire and other hazards. The NEC is widely adopted by states and local jurisdictions throughout the United States, and it serves as the foundation for electrical safety regulations. Staying up to date with the latest edition of the NEC is crucial for anyone working in the electrical industry to ensure compliance and promote safety. Continuing education and training are essential for understanding and applying the NEC effectively. By following the NEC guidelines, electrical professionals can help create safer environments for homes, businesses, and communities. Electrical permits are essential for ensuring that electrical work is performed safely and in compliance with local codes and regulations. Obtaining a permit typically involves submitting plans and specifications for the proposed work to the local building department or electrical inspector. The permit process allows authorities to review the plans and ensure that they meet safety standards and code requirements. Inspections are typically required at various stages of the electrical work to verify that it is being performed according to the approved plans and specifications. Electrical permits help prevent unsafe electrical installations that could lead to fires, shocks, or other hazards. They also ensure that electrical work is performed by qualified and licensed professionals who are knowledgeable about electrical codes and safety practices. Failing to obtain the necessary permits for electrical work can result in fines, penalties, and delays in project completion. In some cases, it may even require the removal and reinstallation of non-compliant work. Electrical permits are an important tool for protecting public safety and ensuring the integrity of electrical systems. They help maintain consistent standards and promote accountability among electrical contractors and homeowners. When planning any electrical work, it's essential to research the permit requirements in your area and obtain the necessary permits before starting the project. Working with a licensed electrical contractor can help ensure that all permit requirements are met and that the electrical work is performed safely and in compliance with local codes. Understanding voltage drop is essential for designing and installing electrical systems that operate efficiently and safely. Voltage drop refers to the decrease in voltage that occurs along an electrical conductor due to the resistance of the wire. Excessive voltage drop can cause equipment to malfunction, lights to dim, and motors to overheat. It can also lead to increased energy consumption and higher operating costs. The amount of voltage drop depends on several factors, including the length of the conductor, the size of the conductor, the current flowing through the conductor, and the type of conductor material. Electrical codes typically specify maximum allowable voltage drop limits for different types of circuits and applications. To minimize voltage drop, it's important to use conductors that are appropriately sized for the load and the distance they must carry the current. Larger conductors have lower resistance and therefore result in less voltage drop. It's also important to minimize the length of conductors wherever possible and to use high-quality conductors with low resistance. Calculating voltage drop involves using Ohm's law and considering the resistance of the conductor. There are also voltage drop calculators available online that can simplify the calculation process. When designing electrical systems, it's important to consider voltage drop and take steps to minimize it to ensure optimal performance and safety. Regular maintenance and inspection of electrical systems can also help identify and address any voltage drop issues that may arise over time. Understanding and addressing voltage drop is essential for ensuring the reliability and efficiency of electrical systems in homes, businesses, and industrial facilities. Calculating conductor ampacity is a crucial step in electrical design to ensure the safe and reliable operation of electrical systems. Ampacity refers to the maximum amount of current that a conductor can carry continuously without exceeding its temperature rating. Exceeding the ampacity of a conductor can lead to overheating, insulation damage, and even fires. The ampacity of a conductor depends on several factors, including the size of the conductor, the type of insulation, the ambient temperature, and the number of conductors bundled together. Electrical codes, such as the National Electrical Code or NEC, provide tables and guidelines for determining the ampacity of conductors under various conditions. These tables take into account factors such as the conductor material, insulation type, and ambient temperature. When calculating conductor ampacity, it's important to consider any dating factors that may apply. Dating factors are used to reduce the ampacity of a conductor when it is installed in conditions that can increase its temperature, such as when it is bundled with other conductors or installed in a hot environment. The NEC provides specific dating factors for various installation conditions. To calculate conductor ampacity, start by determining the continuous load that the conductor will carry. Then, refer to the appropriate ampacity table in the NEC to find the ampacity of the conductor based on its size, insulation type, and ambient temperature. Apply any necessary dating factors to adjust the ampacity for the specific installation conditions. Finally, select a conductor size that has an ampacity equal to or greater than the adjusted load current. It's important to consult the NEC and follow its guidelines when calculating conductor ampacity to ensure compliance with safety standards and prevent electrical hazards. Working with a qualified electrical engineer or electrician can help ensure that conductor ampacity calculations are performed accurately and that the electrical system is designed safely and reliably. Grounding and bonding are essential safety measures in electrical systems that help protect people and property from electrical shock and fire hazards. Grounding refers to connecting electrical equipment and systems to the earth through a grounding electrode. This provides a low impedance path for fault currents to flow back to the source, allowing overcurrent devices to trip and energize the circuit in the event of a fault. Bonding refers to connecting non-current carrying metal parts of electrical equipment and systems together to create an electrically conductive path. This ensures that all metal parts are at the same electrical potential, reducing the risk of electric shock. The purpose of grounding is to provide a safe path for fault currents to flow, while the purpose of bonding is to minimize voltage differences between metal parts. Together, grounding and bonding help prevent electrical shock hazards by providing a low impedance path for fault currents and reducing the risk of voltage differences. Electrical codes, such as the National Electrical Code or NEC, provide detailed requirements for grounding and bonding electrical systems. These requirements specify the types of grounding electrodes that are permitted, the methods for bonding metal parts, and the size of grounding and bonding conductors. Common grounding electrodes include ground rods, ground plates, and metal water pipes. Bonding conductors are typically made of copper or aluminum and must be sized appropriately for the fault current they may carry. Grounding and bonding systems should be inspected regularly to ensure that they are intact and functioning properly. Any damage or corrosion should be repaired promptly to maintain the effectiveness of the grounding and bonding system. Understanding and implementing proper grounding and bonding techniques is essential for electrical safety. Working with a qualified electrical contractor can help ensure that grounding and bonding systems are installed correctly and in compliance with electrical codes. Electrical safety is paramount in any electrical installation or repair work. Firstly, always to energize the circuit before working on it. Use a voltage tester to verify that the power is off. Secondly, wear appropriate personal protective equipment, including safety glasses, gloves, and insulated tools. Thirdly, never work on electrical equipment in wet or damp conditions. Water is a conductor of electricity and can increase the risk of electric shock. Fourthly, inspect electrical cords and equipment for damage before use. Replace any damaged cords or equipment immediately. Fifthly, use ground fault circuit interrupters or GFCIs in areas where there is a risk of electric shock, such as bathrooms and kitchens. Sixthly, never overload electrical circuits. This can cause overheating and increase the risk of fire. Seventhly, keep electrical panels and equipment clear of obstructions. This allows for easy access in case of an emergency. Eighthly, use proper wiring methods and materials. Follow electrical codes and standards when installing or repairing electrical wiring. Ninthly, never bypass safety devices, such as fuses and circuit breakers. These devices are designed to protect against overcurrent and prevent electrical fires. Finally, if you are not qualified to perform electrical work, hire a licensed electrician. Electrical work can be dangerous and should only be performed by trained professionals. Regular electrical safety inspections can help identify potential hazards and prevent accidents. Educate yourself and others about electrical safety practices. By following these guidelines, you can help ensure a safe electrical environment for yourself, your family, and your community. Overcurrent protection is a critical aspect of electrical safety, designed to protect electrical circuits and equipment from damage caused by excessive current flow. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a predetermined level. Circuit breakers are reusable devices that trip and open the circuit when an overcurrent condition is detected. Fuses are one-time use devices that melt and break the circuit when an overcurrent condition is detected. The size of the overcurrent protection device must be carefully selected to match the ampacity of the circuit conductors and the rating of the electrical equipment. Overcurrent protection devices should be installed in accessible locations and clearly labeled to indicate the circuits they protect. Regular testing and maintenance of overcurrent protection devices are essential to ensure they are functioning properly. Electrical codes, such as the National Electrical Code, provide detailed requirements for overcurrent protection. These requirements specify the types of overcurrent protection devices that are permitted, the methods for sizing overcurrent protection devices, and the installation requirements. Overcurrent protection devices help prevent electrical fires and protect equipment from damage caused by overcurrent conditions. They also help prevent electrical shock hazards by interrupting the flow of current in the event of a fault. Understanding and implementing proper overcurrent protection techniques is essential for electrical safety. Working with a qualified electrical contractor can help ensure that overcurrent protection systems are installed correctly and in compliance with electrical codes. Ensuring compliance with the Americans with Disabilities Act, or ADA, is essential in electrical installations to provide accessibility and usability for individuals with disabilities. The ADA sets standards for accessible design in various aspects of buildings and facilities, including electrical systems. Electrical outlets, switches, and controls should be located within reach range for individuals using wheelchairs or other mobility devices. The maximum height for electrical outlets and controls is typically 48 inches above the finished floor. Accessible routes should be provided to electrical equipment and control panels to allow individuals with disabilities to access and operate them. Clear and tactile signage should be provided to identify electrical equipment and controls. Visual alarms should be provided in addition to audible alarms to alert individuals with hearing impairments in the event of an emergency. Electrical panels and equipment should be designed to provide adequate clear floor space for individuals using wheelchairs to maneuver. Electrical codes and standards, such as the ADA Accessibility Guidelines, provide detailed requirements for accessible electrical design. Compliance with the ADA is not only a legal requirement but also a matter of social responsibility to ensure that individuals with disabilities have equal access to electrical systems and facilities. When designing or installing electrical systems, it's important to consider the needs of individuals with disabilities and incorporate accessible design features. Working with an ADA consultant or accessibility specialist can help ensure that electrical installations comply with the ADA requirements. Regular inspections and maintenance of accessible electrical features can help ensure that they remain in good working order and continue to meet the needs of individuals with disabilities. By incorporating accessibility into electrical design, we can create more inclusive and user-friendly environments for everyone. Performing load calculations is a fundamental step in electrical system design to determine the total electrical load that the system will need to support. Load calculations involve estimating the amount of power that will be consumed by various electrical devices and equipment connected to the system. Accurate load calculations are essential for selecting the appropriate size of electrical panels, wiring, and overcurrent protection devices. Electrical codes, such as the National Electrical Code, provide detailed guidelines for performing load calculations. These guidelines specify the methods for calculating the demand load for various types of occupancies, including residential, commercial, and industrial buildings. The demand load is the maximum amount of power that the electrical system is expected to draw at any given time. Load calculations typically involve summing the connected loads of all electrical devices and equipment, such as lighting, appliances, motors, and HVAC systems. Demand factors are applied to the connected loads to account for the fact that not all devices will be operating at the maximum power at the same time. Demand factors are based on statistical data and experience and are provided in electrical codes. After calculating the demand load, the next step is to determine the size of the service entrance conductors and the overcurrent protection device for the main electrical panel. The service entrance conductors must be sized to carry the calculated demand load without exceeding their ampacity rating. The overcurrent protection device must be sized to protect the service entrance conductors and the electrical system from overcurrent conditions. Load calculations should be performed by a qualified electrical engineer or electrician to ensure accuracy and compliance with electrical codes. Accurate load calculations are essential for ensuring the safety and reliability of electrical systems. Overestimating the load can result in unnecessary costs, while underestimating the load can lead to overloaded circuits and potential hazards. Regular reviews and updates of load calculations are recommended to account for changes in occupancy, equipment, or usage patterns. By performing thorough load calculations, electrical professionals can design electrical systems that meet the needs of the building occupants while ensuring safety and efficiency. Electrical drawings and schematics are essential tools for communicating the design and installation of electrical systems. Electrical drawings provide a visual representation of the physical layout of electrical equipment and wiring within a building or facility. Schematics, on the other hand, provide a simplified representation of the electrical circuits and connections. Electrical drawings typically include information such as the location of electrical panels, outlets, switches, lighting fixtures, and other electrical equipment. They also show the routing of electrical wiring and conduit. Schematics use symbols and lines to represent electrical components and their interconnections. They show the flow of electrical current through the circuits and the function of each component. Electrical drawings and schematics are used by electricians, contractors, engineers, and inspectors to install, maintain, and troubleshoot electrical systems. They provide a clear and concise way to understand the design and operation of the system. Electrical drawings and schematics should be prepared in accordance with industry standards and electrical codes. They should be accurate, complete, and easy to read. Computer-aided design, or CAD, software is commonly used to create electrical drawings and schematics. CAD software allows for precise and efficient drafting and editing of electrical plans. Electrical drawings and schematics are an essential part of the documentation for any electrical project. They provide a valuable record of the electrical system and can be used for future modifications or repairs. Regular updates of electrical drawings and schematics are recommended to reflect any changes or modifications to the electrical system. By using clear and accurate electrical drawings and schematics, electrical professionals can ensure the safe and efficient installation and operation of electrical systems. Electrical testing and troubleshooting are essential skills for electricians and electrical technicians to ensure the safe and reliable operation of electrical systems. Electrical testing involves using various instruments and techniques to verify the integrity and performance of electrical circuits and equipment. Troubleshooting involves identifying and resolving problems or malfunctions in electrical systems. Common electrical testing procedures include voltage testing, continuity testing, insulation resistance testing, and ground impedance testing. Voltage testing is used to verify the presence and level of voltage in a circuit. Continuity testing is used to verify the integrity of electrical connections and conductors. Insulation resistance testing is used to measure the resistance of insulation materials to identify potential insulation breakdown. Ground impedance testing is used to measure the impedance of the grounding system to ensure it is providing an effective path for fault currents. Troubleshooting electrical problems typically involves a systematic approach, starting with gathering information about the symptoms and history of the problem. Visual inspections can help identify obvious issues, such as damaged wiring or loose connections. Electrical testing is then used to isolate the problem to a specific circuit or component. Once the problem is identified, it can be repaired or replaced as necessary. Safety is paramount when performing electrical testing and troubleshooting. Always energize the circuit before working on it, and use appropriate personal protective equipment such as safety glasses and gloves. If you are not qualified to perform electrical testing and troubleshooting, hire a licensed electrician. Regular electrical testing and troubleshooting can help prevent electrical fires, shocks, and other hazards. By identifying and resolving problems early, you can ensure the safe and reliable operation of electrical systems. Understanding and applying proper electrical testing and troubleshooting techniques is essential for electrical professionals to maintain the integrity and performance of electrical systems. Power quality refers to the characteristics of electrical power that affect the operation of electrical equipment. Good power quality is essential for ensuring the reliable and efficient operation of electrical systems. Poor power quality can lead to equipment malfunction, premature failure, and increased energy consumption. Common power quality problems include voltage sags, voltage swells, harmonics, and transients. Voltage sags are temporary reductions in voltage that can cause equipment to malfunction or shut down. Voltage swells are temporary increases in voltage that can damage sensitive electronic equipment. Harmonics are distortions in the electrical waveform that can cause overheating and damage to electrical equipment. Transients are brief, high-voltage surges that can damage or destroy electronic components. Power quality problems can be caused by a variety of factors, including utility grid disturbances, improper wiring, and the operation of certain types of electrical equipment. Power quality monitoring involves using specialized instruments to measure and analyze the characteristics of electrical power. Power quality monitoring can help identify the source and severity of power quality problems. Power quality solutions include installing surge protectors, voltage regulators, harmonic filters, and uninterruptible power supplies, or UPS. Surge protectors protect against voltage transients. Voltage regulators stabilize voltage fluctuations. Harmonic filters reduce harmonic distortion. UPS systems provide backup power in the event of a power outage. Regular power quality assessments can help identify and address potential power quality problems before they cause equipment damage or downtime. By maintaining good power quality, electrical professionals can ensure the reliable and efficient operation of electrical systems and protect valuable equipment.